In this tutorial, we're going to be expanding on our previous tutorial's topic, OpenCV agents, but this time we're going to add reinforcement learning into the mix. This tutorial is going to require a few dependencies, one of those being TensorFlow. This is going to be a similar setup to the CPython remote setup for our Anaconda virtual environment. What you want to make sure to do is construct a virtual environment and use the commands pip install and then TensorFlow arguments to install TensorFlow. In this video, I'm going to assume that the dependencies are satisfied and that your virtual environment is set up properly. So I'm going to just jump straight into the code inside of Rhino. So if we just open up our example file, we see that the code structure is similar to our OpenCV agent. This time though, we have two components here, and then we have our import set up from CPython. So our CPython setup is going to be just for accessing OpenCV inside of this CPython component. These two components differ in that one is made to train the reinforcement learning agent, and one is made for deployment or testing of that reinforcement learning agent model. Basically, the way that this is going to work is if we have a point in space and we make a decision, so let's say our decisions include moving to any one of our neighboring pixels, and then we make a decision, so we actually move to one of those pixels, we query whether that pixel is white or black. So if it's black, it's on an edge of the image, and if it's white, it is not, it's just floating in space. After we actually do this movement and querying, we want to feed this into our Keras model for reinforcement learning. We want to reward the model if the pixel we've moved into is black, and we want to punish it if the pixel we've moved into is white. This should keep an agent moving along the edge of a black pixel edge instead of just floating around in this blank white space. The idea here is that you can also layer in other features from the previous agents tutorial. So you can start to coordinate multiple agents in the scene or add additional features to improve the results of the reinforcement learning. But we should be able to get a kind of rough idea of the general setup and how the reinforcement learning agent differs from just the prescriptive one with explicit behavior. We could go a bit more into the structure here as we go on, but for now what's important to note is that general structure. So I'm going to just type it out here so we can visualize that again. So the first thing that we need is going to be three classes. The first class is going to be our RL manager. So this is going to be what actually manages the kind of the reward functions, the state input and output, and a few other features, and actually sends our information over the socket connection. Then, just like our last tutorial, we are going to have a reference image class, and then we need an agent class. So these are our three primary classes. At the bottom, we need to instantiate these. And then after we instantiate them, what we would normally do is run the agent. But in this case, before we actually run the agent, we want to feed in this reinforcement learning model into the loop. So I mentioned before that we actually had a decision to make. So those decisions are going to be called actions. So the actual decision we select is going to be our action output. So usually we would then loop through our run agent function, and this would allow us to run the agent in response to any classes and criteria that we've programmed. But to run this as a reinforcement learning model, we need to run this slightly differently. So there are three things a reinforcement learning model runs on in terms of interfacing with our existing setup. The first is going to be our observations of our environment. So these are going to be called states. And you can say these are observations. And then from those observations, we're going to allow the model to make a decision. And this is going to be called an action. So select decision. These states, by the way, are going to be an input from the Rhino environment. Then our selected decision from the RL model needs to be through the Rhino environment. Those are going to be decided inside of our TensorFlow model and then sent back into Rhino. The last of these things is going to be the reward. So if we made the right decision, if we landed on a black square, then we need a reward. So this is an evaluation of our action. So if the action did something that provided a favorable outcome, then we want to reward the function. Now, a subset of rewards is actually punishments. So if it did something unfavorable, then we can add a negative reward, which will actually punish it. So it's still an evaluation of our action, but it is an unfavorable outcome, and model needs to know to avoid this. A few extra things just to note in the structure, although these are going to be our three primary aspects of the model that we're going to work with. A few other things to note is that we need an end state condition. So this would be things like the agent running in space and then colliding with the boundary, in this case of our screen space or our viewport space. So we don't want it to go past there. So we actually want to add this into the reinforcement learning portion so that it knows to stop or end the episode once it gets to that edge or close enough to that edge. And then we want to reset the initial point. So once it does that and collides there, we would reset the point and then run it again and hope to have a different outcome. So this is going to be an end state, which will check for end state condition. So collision with boundary. And then it will trigger a reset of all agents. Okay, so these are the main things to note for our structure. I'll just leave these in the file and we can go ahead and get started. If we want to, it may actually make sense to just import the OpenCV agent from our last file and we can go ahead and get started from scratch there. So I've copied my component from our last exercise into this file. So if we double click and open this up, we can see that it has the structure for our reference image class, our agent class, and then our agent instances and loops at the bottom. Before we get started there, I'm going to just reference our example components, and we can see that we need two additional features here, or input parameters. We need an R, and this is just going to be a trigger so that we don't always run this component just when we make changes. So that trigger is going to, one, just help us keep the overall file and only run it when we need to, but it's also going to be helpful when we start working with the socket, as it won't just try to connect when the socket stream is not open. So if we hit plus and then right click and change this to R, if we want to, we can even give a type hint that this is a Boolean value. Our other two parameters up here are going to be the same, so an image path and then a set of lines to seed our agents from. And then we can just double click and either type of Boolean toggle, or we could use a button. But in this case, a Boolean toggle is going to be more flexible when we're troubleshooting. And click plus again. In this case, we can call this iterations, but this is going to be our stepping. So how many steps is this actually going to go through? This is going to be a bit different than our typical agent run steps. So usually it would be how many steps are in each agent's trails. In this case, it's actually going to be how long are we going to run this? So how many steps are we going to run this and be feeding in data into our reinforcement learning model? So this is going to need to be way higher than we had for just the agents without reinforcement learning associated with them. So we can just double click and make a slider, and we could just say 100 is less than 2000 and have a slider that goes from 100 to 2000. Maybe for test, we can just keep this at 500 and plug this into iteration. Now we know our iterations are going to need to be integers. So if we just right click here, we can already just do a type hint and select int. This will save us some trouble later on in the tutorial. Then we can just right click in the middle of our component and change this from OpenCV agent to OpenCV RL agent. And this is going to be our train component. Okay, so now we can just dive into the code here. So as we mentioned at the beginning of this video, our structure for this code is going to be three classes. One is RL manager, one is the reference image class, and one is the agent class. So we actually already have two of those classes that are already set up to run the agent based on a reference image, which is great. The only additional one that we need is our RL manager class. So we can make this by typing class RL manager __init self. So inside of our constructor function in this RL manager class, we want two properties to start. These are going to be related to the conditions, the parameters that we are interested in inside of our reinforcement learning models, and connecting those in. So in this case, I'm going to say reward, so sum.reward, and we're going to set this equal to 0 at the start for this class. Then the next two are going to be our states and our actions, which are going to be multiple because we need decisions for each one of our agents that we are feeding them. So self.states, and we can set this equal to a blank list, and then self.set this equal to. Okay, so now we want to start building our functions inside of this class. If we again look at the structure for our RL model, we know that it needs states, which are read from the Rhino environment. So from the Rhino environment, connected using sockets to connect to our PowerShell terminal and run, and it's going to run using TensorFlow in the terminal. So hopefully this is a bit familiar, but the idea is we're going to connect to a socket and pass information on the Rhino environment context of our agent using sockets outside of Rhino into the PowerShell. Then we're going to make a decision effectively in our PowerShell with that script that's running in our PowerShell. And we're going to take that decision, that action, and feed it back into Rhino. And then we're going to update our agent based on that decision. So whatever decision was made, we're going to assign that to the agent, and it's going to move based on that decision. Then we're going to evaluate whether that was a good decision or a bad decision, and then connect to a socket again. And this time we don't need to read anything back into Rhino, we just need to send the reward function into our Python script running in the PowerShell so that it knows whether that decision was good or bad. Then the one last function that we're going to need is an end state trigger or reset, and that should be it for our class. So if we just hit enter, backspace, we can say def send states, feed in self. Right now we're just going to say pass, and then we're going to make send reward, feed in self, pass on that as well. And then we need one last one, which is going to be our end state or trigger or reset, any of those. So in this case, we can just call this reset and feed in self. The first thing to do is going to be set up our socket connection to pass whatever information we have in this, whatever information we have about the state into our terminal, into that Python script that's running. So if you remember in our previous videos, the first thing to do when connecting using a socket is to declare a host and a port. And now we can read in our states. And now we need to convert our states to a string. So string equals string self.states. Now we need to convert those to bytes. So states underscore string dot. And now we need to connect to our socket. So we actually need to import those libraries at the top here. So import socket. And here we can say s equals socket.socket, socket.af, inet, socket.sockstream. Now we need to connect, so s.connect, and we need to pass in our host and our port. And these need to have double parentheses. And then we need to send this, and we need to send our data, so s.send. So we've connected to our socket, now we need to send. So what do we need to send is going to be our data, which is states underscore byte. Okay, so now we've sent that data, states underscore byte. Now we need to declare a new socket. So s now equals socket.socket again. And now we need to connect to a different port. So above this s equals socket.socket, say port 2 equals 8081 s.connect, host port 2, close the double parentheses. And now instead of send, we want to use s.receive. And we need to specify here the number of bytes to expect. So right now we're just going to use a placeholder 1024. But we can check this later and update that number. And then because this will actually output our action, so it's reading this from our PowerShell and bringing it into Rhino, we actually want to set this to action underscore byte, because these are bytes. And then we need to convert those bytes to integers to read, so self.actions equals integer of our action type. And this will now store those action outputs from our reinforcement learning model into the list property self.action. Okay, so that's it for our send states. Now we can move on to our send reward. This is going to look very similar to this top portion. So we can just copy this and then paste it there. The host is going to be the same in this case, but our port, we want to say port 3 just so we don't get it confused with one of the previous ones. And now we can't use 880 or 881, 8081. So we're going to do 8082. And instead of states underscore string, we want this to be reward underscore string, and then feed in self.reward and make this reward underscore byte and reward underscore string dot encode. So we're encoding that reward into bytes after converting it to a string. And now we're calling our socket method. We don't want to use port. Instead, we want to use port 3. And then we're connecting to our socket again. And now we're sending our data, which is not states byte, it's reward byte. And we're going to be using this property reward to send that information using our socket to TensorFlow so that it can update the model according to the outcome of our action. Our trigger reset we're going to come back to in a second. It makes more sense right now to just go into our agent class and start making updates relative to the new structure that we need. The first thing that we want to do on this note is we want to make sure that we are actually calling this class and instantiating an instance of that class at the bottom here. While we're doing this, we can use our new R input parameter, and we can just say if R, so if that Boolean is true, then run everything inside of that tabbed space. And now, in order to instantiate our RL manager class, we can just add this above my image and say my manager equals, and then RL manager open and close parentheses. So we've now instantiated an instance called an instance of RL manager, and we've placed it inside the variable myRL. That's just creating an instance so that we now can call these properties in our init function, but it's not actually doing anything in terms of sending states or reward. So this is where it's going to be important to look back at our reference structure. So the basic structure is we have 3 classes: RL manager, reference image, agent. We now have all 3 of those. We want to instantiate all the classes. Okay, we're instantiating all of the classes. And then we want to run the agent. But we actually want to append this structure relative to our RL model structure. So I mentioned that we are going to read in observations from our Rhino environment. Then we're going to make a decision inside of our Python environment outside of Rhino. And that decision is going to be fed into Rhino to actually run the agent. And then we're going to make this evaluation. So if you type that out, how it sounds, it's going to be state observations class properties, most likely. We need that to be after we instantiate the classes so we can read their properties. And then we're going to send this, so send state observations from class properties. And then we need to receive our action decision. And then we use our action to run the agent. So use action to run agent and evaluate decision, calculate reward, and send to Python and send. Okay, so if this is a kind of pseudocode structure that we want to follow, if we look at our loops down here, we see that we're running through instantiating our agents. Okay, so that seems to be under instantiate, so then we can move down a little bit. So here we just have our call to run the actual agent, which would be this step here, so use action to run agents. So we now know that our state observations from class properties needs to be above line 230. We don't want this to be inside of our loop through the agents because we want this to run for all agents. So we want to read in, so we want to read our state, get the action back, and then run that action in our run move function. So if we go back up to our RL manager class, we can see that our send states function is the one that we're going to want to use for those states in the action step. And that is what needs to be called before we do our run move function. And that needs to happen for all agents, so outside of the agent loop. So we're going to, at the bottom here, use our name MyRL manager. This is going to happen for each of our steps that we're running through, but for all of the agents. So that's why it's outside of that agent. So MyRL manager, and then we're going to call the function send states. And because we're sending our states here, right now our states are going to be empty. The way we have it set up now, our states are going to be empty. So we actually need to find a way of appending to our states in one of these initialization steps. So what we're going to do is actually append it in the construction of our agent instances. So inside our constructor function here, we need to read the context, and we actually have a way to do this in our runMove function already. So we can just select that, copy it into our agent init function, and as an output from this, so querying our myImage, get neighbors relative to our current position, which is going to be our starting position. What we get out of it is our image neighbor indexes, our states, and our image point. So once we actually read those, we want to append them to our list property self.states here. In this case, we need it to be myrlmanager.state. So myrlmanager.states dot. In this case, we want to actually extend it so that it's not just a nested list, it's a flat list of all of the items we're feeding in, which in this case is a list image point, which is our current point, and a list states, which is all of our surrounding neighborhood state. So first extend image point, and then copy this line from states. So now when we run this agent instantiation, we're actually going to be extending the MyRL manager states, and then when we call send states here, we have states to send into our state. Once we're done sending those, we actually want to clear our states, so that way next time we extend that list, which is going to happen inside of our runMove function, we have an empty list. So MyRL manager states equals, and then an empty list, open and close bracket. Now this send states function actually also gives us our actions that we can feed into our runMove, but the next function that we need to call is our reward function. So again, this is not going to happen inside of this agent loop, so we can just tab out and then hit enter. This is going to need to be called after, but outside of that and inside of our iteration loop. So MyRL manager dot send reward. And this is going to send whatever reward we've calculated based on our movements, and it will update the reinforcement learning model relative to that. Now, while we are down here, we can also update our steps. So instead of steps, now we're just going to replace that with iterations. So we can run for however long our slider says. So in this case, 500 iterations. And because it's all inside of our conditional here, it's only going to run when this toggle is set to true. Okay, now we can jump into our runMove function and start working on updating this. So our current runMove is based on several criteria, including trail alignment and seeking neighborhood agents. We actually don't care about these functions at the moment. You can add these back in, but these features aren't important in this tutorial. So I'm going to just scroll up to the top here and change those seek scale and trail align scale. Those properties we're going to set to 0, so it just doesn't factor those in the calculation. Now, if we go back down to runMove, the main image-based decision making that's happening here is happening in this block of code. So this is going to be what we want to focus on in our runMove function. Instead of explicitly stating that we want to find the closest vector to our current heading and then update based on that, what we want to do is actually use our action states here and set our vector equal to whatever our action state output is. So we can go ahead and delete all of this. And now here I'm going to make a note for us to use actions, define and update. So in order to make our actions useful in defining our agent movement, actions are actually just going to output a specific number in this case. And we want to create a list that is representative of all of our potential permutations. So in the structure we're going to be using, an action is actually just going to output a number, a specific number in a range that we specify. So in this case, we're going to look at that action output number as an index value. Now, if all we have is an index value, we need to create a list of all of our possible permutations or potential actions that we can take, and that map or that list, and we're then going to use our action output as an index for that list to grab one particular set of actions or set of movements, one particular permutation, and then use that to define the agent movement. So if we look at this in another way, if we had one agent here and we looked at all of its neighbors as potential movement options, we then get 8 total options that that agent can move. So it could move here, it could move here, 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 any of these. If we had another agent over here, it would also have 8 options or 8 potential moves that it could make. So what we want to do is find all potential permutations of however many agents there are and all of their potential coordinated moves. So let's say this agent moves here and this one moves here. Or let's say they both move there. Or this one moves here. Right? So each one of these are different combinations that we want to create an entire list that is representative of those combinations. And then we want to use our action output as an index for that list so that it can tell us index 4 actually relates to this decision, which is that our agent with index 0 moves to the upper left spot and our agent with index 1 moves to the upper middle position. There are several ways that we can go about doing this, but I'm going to do this by actually creating another function in the RL manager class. So all the way at the top in our RL manager, after trigger reset, we can just hit enter, tab out, and then make a function called capture or maybe compute decisions or compute actions, whatever you want, and then feed in self. And now I'm going to just paste in a kind of pseudocode or explanation on this. So you don't have to copy this, but I think it's helpful to kind of think through the type of logic that we're going through. So let's say we had 4 agents that we were feeding in here. If we had 4 agents, one set of potential outcomes would be that all agents use the neighbor index of 0 to move. So that would be the upper left neighbor. The second option is that all agents could move to neighbor index 1, which would be the upper middle. Then the upper right, all could go to the left, all could go to the right, the lower right, the lower middle, the lower left, the lower middle, and the lower right. So the first 8 are always going to be a series of options in which all agents perform the same movement. Now, after those original 8, because we have 8 potential options to choose from, so that's why 8 is the number there, then it's actually going to be in sets of 4. So for the ninth possible set of decisions, we would have agent 0 goes to neighbor 1, all other agents select neighbor 0. Then we have an option that agent 1 goes to neighbor 1, and then all other agents go to neighbor 0. And then agent 2 could go to neighbor 1, and all others would go to 0. And this type of logic would continue all the way down until every potential outcome has been sifted through and then appended to a kind of decision tree. There's actually Python libraries that allow us to do this without just typing it all out like this. So this is quite cumbersome if we were to actually make these conditionals or append to a list by manually just writing these. Instead, we can work with some mathematical operations to calculate all of the potential permutations from a list of decisions. So before we add anything inside of this function, we need to go up to the top and actually add one more import function, one more import statement. This is going to be from itertools, which is a library for iterating, which is a default library everyone should already have installed, but it will allow us access to some of these iterative operations. So from this library, we're going to import the method permutations. Now, if we copy this down in our compute actions function, we can say permutations, open parentheses, and now what it says here is permutation takes as an input an iterable object and in our object, which is essentially going to be the kind of cluster values. In our case, the first parameter is going to be representative of iterable, so permutations, it's an iterable, and then an R, In our case, it is going to be permutations, and our iterable is going to be our list of potential options. So 0, 1, 2, 3, 4, 5, 6, 7. And this is going to be each index of our neighboring pixel values. So a range from 0 to 7. This could also just be written as range 8. And then our second item, that R, is going to be our length of our agent list, which in this case, we already have something that tells us that, which is our population. So we want to feed in length of population. So we can just add that here, length population, close parentheses. Now what this is going to give us is actually not a list, but an iterable. So we're going to need to do something to this in order to convert it from an iterable, which we can just call self.iterable, and then add this into our constructor up at the top. So self.iterable equals none. And then we're overriding that and saying self.iterable equals the output of our permutations, or all of the potential combinations of 0 to 8 in a list containing whatever our length of population items are. So we can make a new list property called self.list permutations. So that's just going to tell us that this is the list, not the iterable object. So self.list permutations equals, and now in this case, we're going to use a list comprehension method, which there are several of in Python, but we're going to just open brackets and say x for x. So essentially like each item in all items of the list. So x for x in self.iterable. And this will set each item into, this will create a list containing each item inside of the iterable self.iterable. So this converts an iterable object into a list, which we can use later on with index. Now we need to set self.list permutations equal to an empty list in our init. And now we can move back down into our run function, and where we have use actions to define agent movement, we can call myRL manager.compute actions. So what this would give us as an output is going to be all of the potential permutations as a list. So this would be an incredibly long list to sift through. But what we can do is actually call only one permutation, so one potential outcome, using our reinforcement learning action. So we're going to use that as an index, like I mentioned before, and we're going to say myRL manager dot list permutations. So the entire list of all permutations, but we're going to add an index value here to only extract one of those permutations. And this is going to take the index myRL manager dot, so that's our property actions in RL manager. And this is actually not a list, it's eventually going to be an integer, but we can just set it to none in the init. Okay, so now we have one set of permutations, but we have no way of extracting just what our specific agent that this run function is running inside of needs to do. So we would be feeding it what all of the agents need to do and not just specifically what this one needs to do. So what we'd want to do for that is use our index of our individual agent and take that index from this output. So we can say this is a permutation slice. So this is one slice, one subset of our permutations, one potential outcome. And we can say our current index, as in our current neighborhood index that we're going to select based on our action, equals our permutation slice. But we're going to feed in here the index of our agent, which we can say self.agent x. And now we need to make a property called self.agent index. So if we go to our init, we need to add self.agent index, and we can set this equal to index. We then need to pass in this index value in our initialization of that agent. So if we scroll down to the bottom, where we construct those agents, we just need to pass in the index, the position in this loop. So we can change this to for I line in enumerate lines, and we're just going to also pass in comma I. So that I value is going to be our index for our agent. So now what we're getting from this is a single index output, which is going to tell us the exact neighbor that we are going to use to move toward. So now we need to convert that neighbor index to an actual point in space. So target equal, and now we need rs.create point. So we need to create a point and set it equal to our target. And this point is going to be the conversion of our neighbor index into Rhino space. So my image. So I actually have this already written out here, and we can just reference this, but it's going to be my image dot view. So the property view inside of the class my image, which is our reference image class, dot screen client dot coerce 2D point. And instead of neighbor, we're going to feed in current. And we can't pass in this whole thing. This is just an XY value. So we actually just need to pass in the first item and then copy this, hit comma, paste, and just to the second item. So the first one is the X, then the Y, and then our Z is just comma 0, and then close parentheses. So this is actually very similar to how we structured it in our OpenCV agent as well. Now from our target, we want to subtract our current position from our target position, and this gives us a vector value. So target minus self pos equals vec. That vec is computed into the total vec, and then we can set our self.vec equal to total vec. So since we turned off seek scale and trail line down to 0, those aren't going to be calculated in, and we'll just get our vec relative multiplied by its image scale. Okay, so this is almost done for our run function. Two more things here that we want to add in order for this to run. So if we just go down to the bottom of our run function, the first thing we want to do is update our observations. So check out states, then we want to calculate the reward value, and then we want to store our states in our RL. So first, the update our observations. We can just copy the function that we have here at the top, which checks our position. So our myImage.getImageNeighbors, and then we're feeding in our new self.pos that's been updated. And we're getting out of that image input, image neighbors, and state. So now we need to calculate our reward functions. So if myImage, and then we're going to use the property in the class myImage, image, we're going to say my image of the index value image point. So essentially getting the color value at our current position relative to the image. So if this is less than 127, we know we are on a black pixel, which is good. So we want to reward this and say my RL manager dot reward plus equals 0.8. So we're going to add a reward of 0.8 every time our agent lands on a black pixel. Now we can say else. So if we're on a white pixel, my RL manager dot reward minus equals, because we want to punish it if it lands on a white pixel, but we're going to make this a very small punishment, so 0.01. And now we just need to store our states, which is going to look very similar to what we did in the init. So if we just scroll up there to our init inside of the agents where we extended these lists, we can just copy those, go all the way back down here and paste. So now we're just updating our states there. So one last thing that we can add inside of our run function is something that is actually going to check an end state. So this is something that I mentioned earlier, but our end state, so if it collides with the boundary of the screen, we want to trigger a reset. And we want to punish it severely so it does not trigger an end state again. But these are going to create episodes in the reinforcement learning. And we actually already have a function inside of our agent that we made in the last tutorial, which is called check bounds. So we're going to just repurpose this function and use our check bounds as our end state call. So inside of our run move, we can just say self.check bounds, and we're just going to call that. Now, if we go up to our check bounds function, right now we're saying if that check bounds is satisfied, then reverse the vector. In this case, we don't actually want to reverse the vector. We just want to call a reset. So inside of this, instead of the vector reverse, we want to use myRL manager.reward, and we want to say minus equals 10. So we're going to negatively reward that for running into the edge. And then we want to say myRL manager dot, and now we're going to actually create a new property called trigger, set this equal to true because we've triggered our end state. Now we can copy myRL manager.trigger, go up to our myRL manager class and add this as a property. So we've added this as a property. We can change this to self.trigger, and set this equal to false from the start. And now we already wrote in our function trigger reset, but we haven't actually called that inside of our RL manager class. Well, now what we can do is use this self.trigger value, and all the way at the bottom where we loop through everything and we send states and rewards. So right down here, we actually want to say if myRL manager.trigger. So if that, so if it's true, then we want to call myRL manager trigger reset. So if we've triggered the reset, then we need to call that function in order to run the reset. Now we can scroll up to that function and fill it in. So inside of our RL manager class, our trigger reset function. This is a pretty simple function, but I'm going to just comment this out first, and then we can go through actually writing it. So the first thing that we need to do is to loop through agents. For each agent, we want to reset the position to original position. And then we also want to clear the trail points so that we don't remember the trail points for each agent. And then two more things that we need to do. We need to set our reward to 0, and we need to set our trigger back to false. Okay, so that's the general structure. So we can say for agent in population, which is our list of agents, and we can say self.pos equals, and we're going to use here a property called self.home, and we can now make this property inside of our agent class. So right above self.pos, we can just say self.home equals pos. And if we go back into our trigger reward, it's actually not self.home, sorry, it's agent.pos, agent.home. And then if we want to, we can add random values to kind of jitter this. It's in the example file, but in this video, I'm going to just leave it at agent.home. And then we need to clear our agent trails. So agent.trail points equals a blank list again. Then we need to say self.reward equals 0, self.trigger. Okay, and that should be everything. And now I'll just briefly describe a bit of the setup in terms of connection from this component to our TensorFlow. So I'm not going to go into depth into the actual setup of the Python files, but if we just open up our example folder and open one of these Python files in Visual Studio Code, we can just look briefly at what is actually happening here. So inside of this script, we have our import functions, we have a couple of arguments, we have an argument we need to pass in, which is going to be our length of our agent pop. So this is going to be a command line argument, which I'll show you in a second. And the rest of this is going to be the actual setup for our reinforcement learning. Inside of that is going to be a couple pieces, a couple lines of code that actually connect to our sockets and pass this information back and forth. This is already set up, so you shouldn't have to adjust any of this, and we can talk about it on an individual basis, but you don't actually need to know any of this at the moment. If you're interested, though, I'm happy to discuss it. So we should just be able to leave those as they are. The only thing that we do need to change is all the way at the top of the script, so almost to the import statements, just a bit further. So in line 50, we have model save path, and it's right now saved to a path that I've made to a directory called brain. You could also call this models or whatever you want to, but this is where it's actually going to save the weights for this reinforcement learning output. So that's going to be the primary output, and how we actually later use this or actually deploy what we've learned in this training session. So this is really important that you set this path to a path on your computer that you know where it is. So on your hard drive, make sure to change this path. I would leave the quotes, otherwise you'll have some issues with spaces, as I have a space here. The quotes work, but the like apostrophe will not work. So it's not going to be able to read that space. The other thing to note is that our iterations here equals 2000. This should be set to the same as your grasshopper iterations, which ideally you do run a full 2000, but for tests it's okay if they're not the same. I would just leave that at 2000, and it's okay to adjust the slider as needed. So now in order to actually run this connection, we can just hit OK on our component. We can enable these line inputs, right click, set multiple, and then hit enter. So we've now set lines to seed our agents. We have our iteration set to 500, and our toggle is still set to false. This is because we first need to start our loop inside of our PowerShell. So if you just open up PowerShell, navigate to the folder that you have your example Python files in, and then we need to type Python. And since this is our train component, we need to type training.py, and this takes an argument, which just means we're passing in something into our Python file. And we can specify this argument by saying -- agent pop, and then space, and then we're going to give it now the argument to insert there, which in this case is the number of agents. So the number of lines here, which we have 2, so we can type 2. Now we can hit enter. And if we have all the dependencies, we should see some readouts here and then some information about our model, which we see here. And then it says model initialized, start loop in GH client. Now we can double click on our run to set this to true. We actually had an error here because we were trying to convert bytes into an integer. All we need to do is add action_byte.decode, and this will convert it back into a string from bytes, and then we convert it into an integer. Okay, so now we should be able to hit OK, set that back to false, and now we can try and run this again. So double click to run it. One other thing that's causing this error with our socket is that actually inside of our getImageNeighbors function, originally we appended our neighbors themselves. We don't need our current position here, so we can just clear those values. That way it doesn't append the state of our current position, it's just our neighbors to select from. So that now should be good, and we can hit OK. Now we just need to hit the toggle this back to false, and now we need to hit the arrow key up in our PowerShell, and this will access our last run command, which is training.py, and then we hit enter, and now double click to run in Grasshopper. So we actually missed one line here at 208. So when we were creating the point, we were using current index. We want to actually add a line above that says neighbor equals image neighbors of current index, and then we want to feed in that neighbor. We don't want to use the index, we want to use the actual neighbor value. So that was an important mistake. Now hit arrow up and run again. So now it's running, and we can see it looping through and outputting our loss value there, and then eventually it will print out every 8th iteration. It prints out iteration and then our reward value, which we can see right there. So iteration 8 and then our reward value. Okay, and then you would just want to let this continue to run. And eventually you will see that it is actually plotting. Eventually you'll see that it's plotting out some data on how the model is actually training. So we can talk about this in another session. But this is information that it is actually giving to tell you how it's actually performing. And then the other thing is, inside of whatever your directory is for the model weights outputs, you'll see a series of these .h5 outputs, which is the model weights And this is what we're going to read back in order to deploy this. So now we actually want to make this second component as well, which is going to be our test component. So we can just start by copying all of this first component, and we're just going to remove certain functionality from this component. And then it's going to interface with a different Python script in the PowerShell that will actually allow us to read our saved models and run our outputs. So if we just double click into here, there are a couple things that we don't need in this component. So we no longer need anything related to rewards. So we can remove that. We can remove our entire send reward function. We still are going to want to reset with trigger, but we no longer need our specific version of this. So we can actually just delete this as well. We want to keep all of our send states, so leave that how it is. And then we can jump into the agent. So here in the agent, all of this looks good. Inside of our check bounds, we no longer need our reward, but we want to keep our trigger there, so that's good. And then inside of our run move, here we can also remove this portion on rewards, but we want to keep our state updates there. And we also want to keep our check bounds. So now if we go down to the bottom, now instead of calling trigger reset here, what we want to say is actually just break. And if any of our agents have hit the bounds, we just want to stop looping through this entirely. So we'll just say break there, and it will just end looping through. And then we can get rid of our call to reward. And now that should be good, and we can hit OK. Now we can go back to our PowerShell, and instead of Python training, we can say Python test.py, feed in the same argument agent pop and the length of our agent population, which is 2. I'm going to just make iteration from 100 so it runs quicker here. And then in the PowerShell, hit enter, and it should tell us to start the GH loop. Then we can double click to. So this is an important error. I actually forgot for the action states here, the input states and our actions, we need to change our ports. So these are ports used by the other component. What we actually want to do is read 8083 and 8084. This way it just doesn't get confused between each of the components. They're not running at the same time, but this is just going to be helpful for our own notation so that we know what we're sending to which port and keep them separate. So now if we run that again, and then once it says start loop in GH, we can click this Boolean toggle to true, and we can see it's iterating through now our movements. So it's actually taking the model that was trained and it's using that to declare these actions. So action equals 23, action equals 23, action equals 42. And each of those actions corresponds with a movement based on a neighborhood value of each of our agents. So it's the index 42 from our list of possible permutations. So that's it. And then in this case, we can see since we haven't trained nearly enough, it's not actually following the image that carefully. But if you update these parameters and see how it's actually training, you can fine tune this model to actually trace these images pretty well based on observation. Okay, that's it for this tutorial. In the next tutorials, we will look at some of these techniques inside of Google Colab, mainly object detection and OpenCV in Google Colab. And this is going to be a remote computing interface. And it's highly suggested that everyone gets a Google Colab Pro subscription. This is going to make it a lot easier to work on Colab.